This is Algebra 1, Lesson 18A, like terms. We're going to start out with some review math you can see here. Let's do this top problem. We have 2 green smiley faces plus 3 more green smiley faces equals, let's count them, 1, 2, 3, 4, 5. We have 5 green smiley faces. Okay, now before you stop the video and say, wait a second, I know this already, this is easy. We're going to jump to algebra in just a second, but I hope this will help you understand the algebraic concept of like terms. All right, our second one here, we have 1 smiley face here, that's pink, I guess, plus 2 more of them. So 1 of them plus 2 more of them would be 3 of them. Let's look at another one that's a little different though. What if I have 3 orange smiley faces plus 1 yellow smiley face? What do I write? Well, I can't put 4 orange smiley faces because I don't have 4 orange. And I can't put 4 yellow smiley faces. And I can't say I have 4 orange yellows because I don't. Really, I would just say I have 4 orange. Actually, not 4 orange. I would say 3 orange, right? I would have 3 orange smiley faces plus 1 yellow. I really can't simplify that anymore unless I dropped the color names, I guess, and just said 4 smiley faces. So that idea is what you need to understand as we go into like terms. So we'll take another little step here. 4 A's plus 2 more A's. Now, I could have written out A plus A plus A plus A plus A plus A. But you understand that this is 4 A's and this is 2 A's, right? So 4 A's plus 2 A's would be a total of 6 A's. Okay, doing good so far. 3 B's plus 5 B's would be 8 B's. What about 4 A's plus 5 B's? Well, it's kind of like this example up here with the smiley faces, the orange and yellows. We really can't simplify that anymore. These are not like terms. We did have like terms at the beginning. These, we had green smiley faces plus green smiley faces. They're the same thing, so we can add them. I have pinks, and I can add those. But with this example, with the orange and the yellows, they are not like terms. And then when we moved here, these are like terms. I can add A's and A's. I can add B's and B's. But I can't add A's and B's, right? So let's look at some of the technical definitions from the book and see if we can understand those. Like terms are terms that have the same variables. But not only the same variables, but the same variables in the same form or in equivalent forms. We'll look at some examples of this in just a minute. So that the terms, excluding their numerical coefficients, okay, so let's go back for a second here. These are terms. Here's a term. Stop. There's a plus sign. Here's a term. Okay? Let's see. Are they like terms? Well, do they have exactly the same variables? No, they do not. So they are not like terms. Okay? We're not looking at the numerical coefficients. We're just looking at the variables. Okay? So let's read it again. Like terms are terms that have the same variables in the same form or in equivalent forms, so that the terms, excluding the numerical coefficients, represent the same number or numeral, same idea, so we can use number, regardless of the non-zero values assigned to the variables. So what it's saying is things are like terms if they have the same variable, so that if you know the value of the variable or you substitute a value in for the variable, they both are going to have the same value. Now that's kind of not very clear maybe until we have an example. So let's go with an example to help clear that definition up. All right, here's our example. We've got 4xmp minus 2pmx plus 6mxp. So we need to decide, are these like terms? Well, first we see how many terms are there. There's one, stop at the minus. There's one, stop at the plus. There's one. We have 3 terms, okay? Now let's look and see if they are like terms. So we're only looking at the variable, not the coefficients and not the signs. Now, I have an xmp, but here I have a pmx, and here I have an mxp. Well, remember in our definition it said in the same form, okay, variables in the same form, or in equivalent forms. Now we've learned about the commutative property, and we know that you can multiply in different orders and you'll get the same answer. So x times m times p is going to be exactly the same as p times m times x, which is the same as m times x times p. So when the definition says they have to have the same variables in the same form or in equivalent forms, this is okay, because if you knew what these variables stood for, all of these would have the same value. The variable parts would have the same value because it doesn't matter what order you multiply things in. Okay, so let's look a little bit more. Let's say, same example here, we're just taking the variable parts. Let's say that x is equal to 4, m is equal to 2, and p is equal to 6. So I'm going to put those values in. And then here the p is 6, m is 2, x is 4. They're written different order, but the same numbers, aren't they? M is 2, x is 4, and p is 6. We can go ahead and start. 4 times 2 here is 8, and 8 times 6 is 48. So the value of xmp is 48. Now, we know we have the same numbers here. We have a 4, a 2, and a 6. We have a 4, a 2, and a 6. So we're going to get 48 here as well. And then we have a 4, a 2, and a 6. So we know here we're going to get 48 as well. So all of these have the same value. And since they have the same value, then I could combine these, which we will learn in a future video. But right now it's enough to know that these are like terms. They have exactly the same variables written in equivalent forms. And like we said, you will be able to combine them in the next video.